Welcome to this early morning wake-up call slot. My name is Martin. I'm currently working at Dresden University of Technology, and today, I'm going to present the research results dealing with the enhancing of aircraft ground trajectories. So the complete title is shown here on the first slide. And as you can see, two core objectives. The first one is about generating ground trajectories from sparse ADS-B data, and the second one is dealing with a stochastic pavement roughness modeling. Okay, let's have some introducing words about the background. So with increasing flight movements, we expect more complex airport ground operations. And this is leading to more frequent braking, acceleration and turning maneuvers of aircraft, and thus impacting the load dynamics on the aircraft structure, especially the aircraft landing gears. Currently, the maintenance of aircraft landing gear is based on fixed cycles, and between these cycles, nobody knows what is the state of the aircraft landing gear. And with digital twin technology, enables monitoring during ongoing operations, especially concerning stress and fatigue. And the digital twin can be used for prediction as well. Our concept is about the development of a load monitor within the context of a digital twin framework. And this is especially focusing on the aircraft ground maneuvers. And for this, we are developing an sophisticated simulation environment for determining the accelerations and forces acting during ground maneuvers. And in this case, we have to consider different factors like aircraft design, flight operations, weather, and so on. Okay, this is just a basic overview over our load monitor. So as you can see here, we have three fundamental modeling packages. The first one is about the aircraft structure model, and it contains an tire model and a landing gear model with the audio struts. And as you can see here, the airframe is grayed out since we assume a rigid body model. The second package is about the aircraft motion. So here we have the aircraft movement itself and the trajectory. And the third part or package is about pavement modeling and dealing with roughness. Roughness can be described as irregularities in the surface of taxiways and runways. And of course, the condition of the areas, for example, wet or dry runways. Today, I'm solely focusing on the trajectory part and on the roughness part. This is just a comprehensive overview of the different modeling packages. And as you can see, the four main packages are here incorporated in our aircraft motion model, which is able to calculate the landing gear loads during ground operations. And this can be used for diagnosis and prediction. Okay, let's have a short look on the scope and the objectives. So concerning the trajectory, we aim to model an accurate trajectory with a smooth transition, especially in the curves, because we want to translate the trajectory into steering inputs of the nose landing gear. And here, therefore, we used open source ADS-B data. And as all of you know, this data can be sparse or faulty with a low resolution. On the upper right image here, you can see two different trajectories. So the blue one is a complete trajectory for a good data set, ADS-B data set with a high resolution. And the red one is a typical sparse ADS-B data set. And as you can see here, the trajectory is running through the green and cutting the taxiways. Concerning pavement, the roughness is defined or characterized by design-related features and damage patterns. So on the right side, you can see different examples for design-related features, for example, runway grooving or inset lights. And below you see typical damage patterns. Here as an example, alligator cracks and so-called pop-outs. The pavement or the roughness significantly affects or influences the tire surface interaction. And current roughness data is rarely published and is mostly outdated and is dealing with worst case data sets. Just for an example, according to the certification specification for large aeroplanes published by EASA, we have a sample roughness data set going back to the 1950s. About our objectives concerning trajectory, we developed a method for modeling or processing an aircraft ground trajectory from sparse ADS-B data, and we used a map matching approach for this. And concerning pavement, we want to model different surface roughness profiles, and here we use a stochastic modeling approach based on the so-called power spectral density, PSD. Okay, next slide. Concerning data sources. As already mentioned, our trajectory or the aircraft side is modeled by using an ADS-B dataset derived from OpenSky Network. Here for our reference aircraft, Airbus A220 or at Frankfurt Airport. Concerning airport infrastructure, we use geospatial information derived from OpenStreetMap. Contains, for example, runway and taxiway markings, as well as type of the pavement and the designators. The pavement is especially focusing on the so-called macro texture. So on the image here below, you can see the difference. So the micro texture describes the features or the texture of a single stone, and the macro texture is the texture among different stones. In this case, we utilize the so-called power spectral density, and this is an analysis of the frequency content of surface, providing detailed insights into roughness distribution and enabling the assessment of the macro texture across spatial frequencies. And as a second step, we insert different irregularities, as already mentioned, separated into design-related and typical damage patterns. And this data is derived, the design-related features, from infrastructural requirements published by FAA, for example, and the damage features like cracks or pop-outs are derived from regulatory maintenance inspections and in-situ analysis made by FAA, US Army Corps of Engineers, and Transport Canada. Okay, now let's have a look on the methodology. This is a general overview, and as you can see here, we have the two packages, the trajectory model and the pavement model. Concerning the trajectories, we first have to pre-process the OpenSky Network and the OpenStreetMap data. And from the OpenStreetMap data, we are generating a graph model with nodes and undirected edges. And this graph model is used for the enrichment of the ground trajectory. And after we have enriched the trajectory, we can calculate specific movement parameters like ground speeds and something like that. Concerning the pavement model, we first have to create the so-called base surface, which describes the macro texture of the surface, as already mentioned, by using the PSD method. And then we have to define pavement material distinguished into asphalt and concrete pavements. And we have to define a damage rating. After creating the base surface, we can insert our irregularities, in the end leading to a complete pavement profile for the enriched trajectory. Okay, now let's have a closer look on the methodology, starting with a trajectory. What you can see here is our base layer. This is an extract from the airport of Frankfurt. You can see here, for example, runway 25 left, runway 25 center, the parallel taxiways, the different exit taxiways, and of course, the apron area with the gate and the remote parking positions. Now we put in the original OpenStreetMap data, distinguished into runway, taxiway, and the parking positions. And as you can see here, between the data points, we have huge gaps. In order to create a graph model, we have to fill up these gaps. And here we are, so we're doing this by using linear interpolation, leading to this picture here. As you can see, the gaps are filled. We have with the circle the original OpenStreetMap data, and the dots represent the extended OpenStreetMap data. This is just a more detailed view, and you can see here we have a good set of data points describing here the runway and taxiway centerline markings. Okay, this data is the basis for our graph model. What you can see here are the grid points for the graph model derived from the extended OpenStreetMap data. Yeah, this shows a more detailed view, and here you can see that we have equidistant grid of points derived from the OpenStreetMap data. For creating the graph model, we have to do specific processing steps. At first, we calculate the Euclidean distance between all grid points. And for setting up the graph model, we create valid connections with two constraints. The first one is that the distances mustn't be zero, and we are grabbing the data points for the graph model within a search radius of 10 meters. And by doing this, we get this graph model, what you can see here. So this contains of nodes and undirected edges. As you can see here, especially in curved sections, we have some connections which are not used, but this is a fact we have to improve, or we improved here in the paper of the OpenSky Symposium. Okay, so the first part of our methodology is done. Now let's come to the enrichment of the aircraft ground trajectory. At first, we create an overlay. What you can see here with the red squares is a typical OpenSky data set with sparse data. You can see it especially here in the curved sections with the cutoffs. This is a more detailed view, and you can see here the trajectory, if you connect the data points, is sometimes going through the screen. So for getting an enriched and smooth trajectory, we are now applying our matching approach. So at first, we assign the tracked aircraft positions here given by T with the nodes of the graph by applying the shortest Euclidean distance. Secondly, we calculate the shortest path between two mapped nodes of the graph by formulating this optimization problem. So we have the aircraft position 1, aircraft position 2, and now our algorithm fills up the gaps along the graph in order to get a smooth trajectory. So this is the final result of our enriched trajectory. In red, you can see the original data points, and in blue, our enriched trajectory. So this is just a general overview. And as you can see here, we have a good and smooth trajectory, always being located on the center line of the runway, respectively the taxiway. In order to have a smooth transition, especially when putting the trajectory into our aircraft motion model, we applied additional filtering techniques. And for our task, we found that the Savitsky-Golay filter works best. So Xavier, maybe this is a good add-on for your filter library. And as you can see here in the original enriched trajectory in red shows some sharp edges. And with applying the filtering, we have a good and smooth transition between the different segments of the trajectory. Okay, now some words about the outcome. So in the end, we get a more detailed trajectory, and yeah, this enriched trajectory can be used within our aircraft motion model for further analytical investigations. And the methodology's effectiveness is especially evident in curved sections, and now we have a smooth transition without any cutoffs or something like that. Okay, now let's have a look on the last part of the methodology for the trajectory generation. So by using the enriched trajectory, we are able to calculate specific maneuvering parameters, for example, the ground roll distance, our average segment speeds, and the heading change. And especially the heading change is used for our trajectory segmentation. So we are able to separate our trajectory into straight and turning segments. Additionally, it's just an add-on, we are able to allocate the air operations area designators from runway to taxiway and to parking position. So this looks like this. Here we have our enriched and smooth trajectory. And now we are able to define the segments along the complete ground track, distinguishing into straights, right turns, and left turns. Additionally, we can allocate the designators. In this case, our aircraft is landing on runway 25 left, proceeding on taxiway Mike 17, Mike, Tango, November East, November, and finally reaching its parking position, Victor 111. So our lights green now for this part of the modeling approach. Now let's have a look on the pavement model, starting with our so-called base surface representing the macro texture of the trajectory of the surface. Okay, let's start with creating the base surface. So here at first we have to define a grid given by a specific length and width, and the degree of resolution is determining the number of nodes. So for example, if we have a pavement surface of 1 square meter with a resolution of 1 millimeter, this results in a total of 1 million nodes. And the gray is here showing the basic grid. Now we insert the base surface. At first we have to define the transversal and the longitudinal slopes of the surface, and then we utilize this fancy equation here for artificial fracture structured surfaces by using the power spectral density. And what you can see here in the result is this base surface defining the macro texture. This base surface is now implemented into our grid. And now we are done with this first step here of our pavement model. The second step, setting the scene. So at first, as already mentioned, we have to define our pavement materials. So this is distinguished into flexible and rigid pavements. And secondly, we have to define the design and operational related irregularities. So for example, concrete joints, insert lights, grooving, and rubber abrasion, especially being located in the touchdown zone of a runway. The third step incorporates the definition of the pavement damage rating. Currently, we are using a pavement condition index logic, and here we have details about the damage type, the damage quantity, and the damage severity, leading to in the categories from A to C. So A is a very good surface, and C is a bad one. This is just an overview which irregularities are implemented in our current algorithm or current model version. So distinguishing into asphalt and concrete. And for example, we can implement cracks, slabs, rotting, heaving, and something like that. And on the lower part of the table here, you can see again, the implemented design or operational related irregularities. Okay, this is just a detailed view how this looks within our model. So on the left side, you can see a typical pattern for concrete slabs, and the lower part of the image shows a detailed view of such a concrete slab with a filling on the bottom. On the right side, you can see a typical damage pattern. You can see especially at concrete pavements, the so-called pop-outs. Okay, now we have to insert these different damage patterns and irregularities into our base surface, into the macro texture. This is done by a randomized approach. At first, we have to define an initial point, shown here with dsx and dsy. And then we can define the damage rating, defining the quantity and the severity according to our damage category. So just an example, if the surface is rated as category A, and we have a concrete pavement, then for example, the damage pattern here, the slab settlement, has a quantity of about 5% of all slabs and a severity of up to 5 millimeters vertical displacement. Now we come to the implementation of the different irregularities. So just for an example, a crack is defined by its width, by its length, by the quantity, and by the elevation. And the elevation can be calculated by this equation here. So just for example, a crack in a concrete surface rated as category A has a depth of about an elevation of 5 millimeters to 10 millimeters. And then this elevation value set here is iteratively applied from the initial point, spreading randomly across subsequent nodes within our grid of the base surface. This process continues until a specific damage quantity, for example, 5%, is achieved. And in the end, we have to update the elevation spectrum of our base surface by applying our elevations of the irregularities. And what you can see here is just an example how this crack spreads through the base surface. Okay, now again, online screen, both parts of our modeling approach are finished. Now let's have a short look on the results and the conclusion. So what you can see here is our final enriched trajectory for an exemplary flight here of an Airbus A220-300 landing on runway 25 left at Frankfurt Airport. The colored data points show the smooth and enriched trajectory, and just for comparison issues, you can see in red the original ADS-B trajectory. Furthermore, you can see here the average speed in each segment and the heading of the aircraft along the complete ground trajectory. Concerning the roughness, we modeled our surface in 3 different sections. So the first one is on runway 25 left with a distance of about 2,000 meters, reaching from the touchdown point to the exit. The pavement material is asphalt. We have an upslope and downslope, of 0.3% and centerline inset lights. And afterwards, we are modeling the taxiway Mike 17 to Mike with asphalt pavement as well and inset lights, followed by the section to the apron here with concrete pavement and again, centerline inset lights. And what you can see here on the right, again, our trajectory. Then here we have the elevation profile along the complete trajectory. And on the below, this is the resulting surface, our roughness. Just for illustration purposes, these red peaks here are the inset lights. On taxiways, they normally have a distance, I guess, of about 30 meters. And just for illustration purposes, we decreased the distance a little bit. Okay, now let's summarize the results. With our methodology, we are able to reliable process ground trajectories even if the database or the data points are sparse, with applying map matching and smoothing techniques, leading in the end to a more realistic trajectory, which can be applied within our aircraft motion model. Concerning roughness, we stochastically model our surface roughness profiles by using the power spectral density, and we are able to integrate design-related irregularities as well as typical damage patterns. This roughness generation is or leads to a comprehensive roughness profile and is also able to model isolated irregularities, so-called single events, spanning from credible cases to worst-case scenarios. And of course, our methodology is entirely based on open source data. Okay, now some closing words concerning the outlook, our future works. So at first, concerning the trajectory modeling, we have to validate our approach by comparing our enriched trajectories to trajectories derived from more precise data in order to calculate position deviations. So for example, we can use data from the flight data management system or the the meantime famous STEX data derived or recorded at US airports. We have to implement the ground trajectory into our aircraft motion model, and then we are able to interpolate between the data points in order to get realistic acceleration and speed profiles. Of course, we can, we have to do some statistical processing derived from our enriched trajectory, in order to use this approach for trajectory prediction. So, for example, we can model probability density functions for different aspects like speed in turns and something like that. Concerning roughness, we have to refine a little bit the input coefficients for the base surface, and then we want to compare our surface profiles with realistic or real profiles provided, for example, by the software Pro FAA in order to calculate various pavement indexes and especially vertical accelerations. And in the end, we have to select an appropriate tire model according to the modeled roughness profiles, considering the frequency range of the different tire models. Okay, that's it from my side. Thank you very much. And now I'm open for questions.
Hello, nice work. When you do the processing of trajectories on the apron, are you snapping your, let's say, sparsely sampled trajectory to the taxiways? How do you handle the sparseness in position report?
Especially on the apron. Yes. Okay, so where we have a lot of different center lines, especially for the parking positions. The bases are the open street, or is the open base is the open street map data, and we are doing this map matching as in the as well in the apron area, but we found some problems, especially in apron areas where you have a lot of different center lines, and I think we had 290 trajectories, and maybe 10 of the 290 trajectories, our algorithm wasn't working. So it was jumping, but this can be refined by processing the centerline data. So by deleting, for example, overlapping centerline markings. But this is indeed a problem.
Thank you very much. It's very interesting. I think this is great. Like ground data, like having a proper motion model would be great. I'm wondering how scalable is this? Like how easy is this to do this for 1,000 ADS-B flights, or for example, to include this in traffic and I download a flight and it automatically smooths my ground trajectory?
So the computational time isn't a problem. So our algorithm is really fast. What takes time is setting up the graph model, for example. But if you have calculated the connections once, you can store it in a separate file, load the file, and then this is a really fast algorithm.
Wow, that's fantastic. Thank you.
But to be honest, I haven't tried to calculate 1,000 or 10,000 of trajectories.
Good morning. Quite interesting work, by the way. One thing, you have said that your algorithm doesn't work properly because on the apron area, because doesn't assign in a number of cases, 10 cases, or something like that, which are the center line that the aircraft are following. You check operationally if what happens is that the aircraft is not following the center line at all?
Sorry, I didn't get the question.
I mean, you say that sometimes there are so many center lines on the apron area that your algorithm is not able to follow if it is in one or another center line. To check operationally if the aircraft is exactly following the center line?
I think we have to distinguish into straight segments and turning segments. So on straight segments, the pilots should stay on center line, and in curves,
should.
Yeah, but I think there are a lot of centerline deviation studies, for example, at JFK Airport, and you can see there that we have just a few meters deviation only under specific conditions. And of course, this is a discussion related to human performance. So each pilot is steering the aircraft in another way. But more important are the curved sections. So we have two common methodologies. The first one is the cockpit over centerline, which is the standard procedure, and the second one is the so-called oversteering method. The oversteering method cannot be modeled with our approach because we are filling up only on the center line. So we have some operational special cases where this methodology is limited.
And I'll ask one brief question, and then we'll head over to our next speaker. Can you speak to the completeness of the OpenStreetMaps at other airports, or was this just one that happened to work out well?
No, it's an international database. We used the Overpass Turbo API, so it's an open source API, and you find OpenStreetMap data of airports all over the world. This database is still growing and is improving. And so everyone is able to specify or define additional components within the airport. So this is, so to say, living database.
And do they tend to label the taxiways?
Yes.
Excellent.
And that's why we are able to designate the AOA designators, or to apply the AOA designators. But there are sometimes some faulty data in it, but you can compare it to the official AIP publications in order to improve the data sets.